Hi grade 12s, this is JP. Today we're going to look at some of the applications of calculus, and the most important part here is optimization. So when you're going to be presented with a question and they ask you to find the maximum area or find the minimum area, or maximize this, minimize this, optimize it, find the least possible area for a certain constraint. So this is to do with optimization, and it's just part of calculus, and it's a beautiful section. So calculus enables us to solve real life problems where we would normally just guess and check, and we don't have an algebraic approach to solving this, and this enables us to actually to find a definite answer to what will be the best possible case or the best scenario given a certain constraint. Okay, so whenever you see these words like maximize, for which it will be maximized, minimized, optimized, for the least or the greatest possible area, this is all to do with optimization. And the most important part here, and I'm going to start off with that, is we need to be able to find the optimized function. So that's the big deal. The rest is quite easy. To optimize means we want to find the maximum or the minimum value. Right. In other words, if remember, how do I know where the maximum or minimum value is? It's those x. It will shoot out those x values when the first derivative is equal to 0. That's the important part. So it will be, so example, that x value and that x value, right? So a2 and a1. It's for those two x values where there is a minimum or maximum, and then we're just going to check with the second derivative test. Remember, when it is concave up or down, whether it's a minimum or a maximum. Okay, so we'll go through all of that. Okay, so let's start off with an example. Determine the maximum value of a certain optimized function. So the function like a is equal to x plus by 16 over x minus 2. Okay, so you've been given the function, so that's quite neat. So you just have then a to the power ax, like f of x, right? So this is now just the subject is a, and it's we're finding in terms of x plus by 16 over x minus 2. All right, and what we're going to do is to find the maximum or minimum. Of course, we're going to find, that's just finding the the first derivative. Sorry, so you're going to find the derivative of that. In other words, we're going to say, well, what is going to be the derivative of a to the power of x? Okay, remember there's a couple of things that makes it a bit difficult for us to find the derivative. One is if x is in a root, the one you're finding it with respect to, right, is in a root, and the other part is where it's on the denominator. So it's probably best to first rewrite this question as ax is equal to x plus by 16 to the power of x minus 1 minus 2. Remember that from back when we started off with derivatives, right? Good. And then we're just going to find the derivative then. So what's the derivative of x? That will be 1. What's the derivative of 16x to the power of minus 1? That will be minus 16x to the power of minus 2, right? Multiply the exponent to the coefficient and minus 1 from there. And then what's the derivative of minus 2? What's the derivative of any constant? That will be 0. So therefore we've got a to the derivative of ax is going to equal to 1 minus 16 over x squared. And what do we do then to find the maximum or minimum value? That's what we're going to let the derivative. That is where the derivative of that optimized function is equal to 0. In other words, 0 is equal to 1 minus 16 over x squared. Therefore, 16 over x squared is equal to 1. That means x squared is equal to 16. That means x is equal to plus or minus 4. Right, so we need to determine now whether plus 4 is the maximum x value, whether it will give me the maximum x value, or negative 4 is going to be the maximum x value, or which one is the minimum. So how do we check it? Be careful of just looking at the y values. So I've chosen this example specifically for that reason. Right, so how do we know whether 4 is the minimum or whether minus 4 is the minimum? be very careful of just looking at the y values to make that decision. All right. I know in a cubic function, you just look at the y value. The one with the highest y value, of course, is the maximum. The one in the with the lowest y value is the minimum. Okay, so that's quite straightforward. But of course, this is not a cubic, and not all functions are cubics. So what do we do? The second derivative test, I do think is so critical. So let's quickly see what happens. First of all, if we consider the y values, I just want to make that point. So in other words, if I substitute 4 into all the x's, you're going to get 4 plus by 16 over 4 minus 2. So a of 4 is going to equal to 4 plus 4 minus 2 is 6, right? And if you substitute minus 4 into there, you're going to get, what's that, 4 minus 4 minus 4 minus 2 is minus 10, it looks like. So in other words, this is the point 4 and 6, and that is the point minus 4 and minus 10. So at first glance, this would look like, well, at negative 4, you're going to get a minimum value, right? Because negative 10 is much lower on the the y value. There is much less than 6. Do you follow? So at face value, that it looks like the point 4, 6 must be a maximum. I mean, if you just consider this on a Cartesian plane, 4 and 6 would lie there, right? And negative 4 and 10, negative 10 would be like this. You would think like, oh, of course, man. Of course, it's obvious. That's the minimum and that's the maximum. It's obvious. Now, be careful of obvious. Okay, so I don't know if you remember, hopefully you remember, with the second derivative. So let's just have this part now, yeah? So if in a function, if you look at the second derivative, if it's equal to 0, that's the point of inflection, right? So if the second derivative, okay, at a specific x value, is greater than 0, that means it's a smiley face part of the function there, and it would mean that that's a minimum turning point, right? And if the second derivative at a specific x value is negative, that means that part would be a bit down, and then that would mean you've got a maximum turning point. Okay, so what we're going to do now is, of course, we're going to work out what the second derivative is. Let's just minimize that a bit. So our original function was ax is equal to x plus by 16 over x minus 2. Then we said that, okay, the first derivative we worked out earlier, it's like there, is equal to 1 minus 16x to the power of minus 2. So that would mean the second derivative, so that's the first derivative, the second derivative therefore would mean that is equal to 32x to the power of minus 3, right? Multiply minus 2 to the minus 16 and minus 1 from it. Okay, so that's the second derivative. So that would mean so that's the same, of course, is 32 over x cubed. Okay, why is this important? In other words, if I would substitute into the second derivative an x value, and that answer is positive, all right? That means it's a minimum turning point. Do you follow from this part here? So, and if I substitute into the second derivative an x value, and that answer is negative, that implies it's going to be it's going to be a maximum turning point. Okay, so let's go for it. So if I substitute now, let's say 4 into the second derivative, that will be 32 over 4 cubed, right? Which means that is 32 over 64, okay? Don't worry what the answer is. We're just concerned about whether it's positive or negative. And that would mean 32 over 64, that means that is the second derivative there is greater than 0. What does that imply then? Well, that means it looks like that, right? And what does that mean? That means there's a minimum stationary point. And the same story, if in the second derivative, if I substitute minus 4 into there, you're going to get 32 over minus 4 cubed. Okay, and of course that answer would be negative because minus 4 cubed is minus 64, right? So that answer is negative. That means it's a down face parabola, like Joe's face when he sees me. And that would mean there's going to be a maximum turning point. All right, So actually what happens here is, that's quite interesting, isn't it? So because do you see 4, 6? 4 is much, the y value is much higher there, but that is actually, according to the second derivative test, if you substitute 4 into there, you get a positive value, the second derivative is positive there. That means it's a minimum turning point. So that is actually a minimum turning point there. How the hell is that possible? And the same story, if you substitute minus 4 into the second derivative, you get a negative answer, right? That means the second derivative is negative. That means it's concaving down. That means it's a maximum turning point. So that part there is a maximum turning point. Oh my greatness, what is going on? Let's quickly look what happens here. Do you see what that's the real graph of this function? So although this y value there, although this y value there is, so that's y value is at 6, and that y value is negative 10, so you would think, okay, that y value is much greater than the other one, so therefore that should be a maximum. No, it's not. This is the minimum part of that function. It's the minimum part of that function. And in the second part, right, that is the maximum part of that function. It's a split function. So the AP students have done rational functions there, and we know about even and odd functions, but hopefully they know something about that. So yeah, so be careful of just saying, well, this y value is higher than the other one. It depends on how that function would look like, of course. That will be a maximum, and that will be a minimum. All right, so this is quite critical. Okay, so what have we done so far? So I'm going to show now how to find that optimized function. It's not been given to you, but so if I present you with an optimized function, I ask you to find the minimum and the maximum. You find the derivative of that function, right? You equal it to 0. You find those x values. What do you do then? You need to check, right? And how do I check? Well, if you check with the second derivative test, if you find the second derivative and at those specific x values, right? If that is, and then there's two options. If the second derivative at that specific x value is negative, that means it's a concave down. That would mean that's a maximum stationary point. It's a maximum value. It's the highest it's going to get, right? If you're finding the second derivative at that specific point, right? And that answer is positive, that means it's a concaving up part. That means that's going to be the most minimum value that function is ever going to get. All right. Right, in most cases, you are going to be given certain constraints, okay? Or certain parameters, all right? So you're going to be given this. I'm going to do a lot of examples then. Then you're going to, they'll tell you there's, I don't know, some perimeter, or there's, I don't know, the area of something, and okay, but then so a certain parameter, sorry, and then what you're going to do is they're going to ask you to optimize something. So in other words, to find the minimum area or the minimum volume or the minimum total surface area or something. So there's optimized function, right? Or optimized function. That's his function, and and so most cases, in probably 90% of the cases, that was just made up, but anyway, by far the majority of the cases, there's going to be some simultaneous equations going to be involved there. Right, so between the constraints and optimized function. Your optimized function, right, the one you want to find, okay, must only have one variable. You're finding that variable, just for the core syllabus, you're finding that variable with respect to 1. It's like an x. There should only be x's. Okay, so that's important. So there must only be one variable. And you can give, if they don't tell you what that optimized function should be, you can give it any value. You can make it all ax's, it doesn't matter, okay? But they must, what's very important there, this must all be just in terms of x. Why? Because we want to then find the derivative. When we optimize that function, we want to find it with respect to that one variable. In other words, with respect to x, if there's x's or something. All right, so this is a very important part. But I know some of you are going like, what the hell are you saying? I think it's best to actually just do a couple of examples, and you'll see it's actually that bad. I'm going to do a couple of examples with you now. So what I would encourage you to do is, or maybe first follow the first one with me, and then So after I've read the question, or you can read it, you just pause it, you try it on your own, and then you just play it again and you watch that last part. I really would encourage you to pause it and you try it. Our objective now is, the rest is quite easy. The most difficult part of this is just to find the optimized equation. Once you've got that, the rest is, it's plain sailing. There's nothing to it. Okay, let's go for it. The sum of two positive numbers is 10. Okay, so we don't know the names of those numbers, but let's just say it's x plus y, the sum of those two numbers, that's equal to 10. One of the numbers is multiplied by the square of the other. So if I say, for example, x times by y square, right? Okay, the one of the numbers is multiplied by the other one. So you could also have said, well, it is y times by x squared, right? I mean, there were no specifics around that. If each number is greater than 0, find the numbers that make this product a maximum. Okay, so let's start. What do you have? You've got this parameter in place, this constraint. Okay, so parameter in place is x plus by y is equal to 10. Okay, so that's what you've got. They present that to you. Now you're asking, okay, so what is my optimized function? My optimized function, what do they want me to find, to optimize what? They want to know, find the numbers that make this product a maximum. The product a maximum. The product is this part there. So for example, you can name it like px for the product is equal to xy square. Okay, x times by y square. Okay, and of course that's, I mean, if you can make it ax, bx, dx, I don't know. I don't mind. Okay, here we go. So that's what. So you've been presented with some parameters, and then you've got your optimized function. All right. So what we're going to do is but the optimized function, remember I told you, must only be in terms of x or in terms of y. So you need to choose one of those two. In other words, what do I need to do? I need to do simultaneous equations. All right. So what we've got is so px is equal to xy square, and then we've got, so this x plus y is equal to 10. We either need to get x alone or y alone, right? Doesn't matter which one you're going to get. So if you, for example, say y is equal to 10 minus x, just to be a bit more difficult, so is x then is equal to 10 minus x, right? So the value of y, the value of y is equal to 10 minus x, and you square that, so therefore px is equal to x times by 100 minus 20x plus by x squared. So therefore px is equal to 100x minus 20x squared plus by x cubed. Right? Hopefully that makes sense. And then what? So that is now our optimized formula. The formula, the function, the optimized function. And what we're going to do with that now, the rest is quite simple. What we're going to do with it, we're going to work out what the derivative of px is and equal it to 0 and find those x values. Okay, so what is the derivative of p here? It's going to be 100 minus 40x plus by 3x squared. So therefore 3x squared minus 40x plus 100 is equal to 0, and you can either use the quadratic formula or you can factorize that. I think it actually factorized quite nicely. It's 3x minus 10, x minus 10, but of course, seriously, you can use the quadratic formula for that. So therefore 3x minus 10 is equal to 0, so 3x is equal to 10, x is equal to 10 over 3. Or what we've got is we've got x minus 10 is equal to 0, so x is equal to 10. Okay, so which of these two would it now be? So is it x is 10 over 3, or is it x is equal to 10? Well, they actually told us in the beginning that both numbers, there we go, if each of those numbers must be greater than 0. Okay, so we need to find y in each of those. For x is equal to 10, if you find y, right, so what we can do is then you can say 10 minus x, 10 minus 10, therefore y is 0. Okay, but 0 is not greater than 0, right? So this can't be. So it can't be 10. The one number can't be 10, the other one 0. if x is equal to 10 over 3, y then is going to equal to 10 minus x, and x is equal to 10 over 3. So that is equal to 30 over 3 minus 10 over 3, which is equal to 20 over 3. Okay, so if x is equal to that, y is equal to that, and that looks like the right solution. Okay, so let's just double check these answers. I think it's a good habit to double check them. The second derivative, okay, so our function was, what again? Optimized function was this baby, yeah, all right? So it's 100x minus 20x squared plus x cubed. Then we said our first derivative was equal to 100 minus 40x plus 3x squared. Our second derivative, therefore, is going to equal to minus 40 plus by 6x, okay? So don't let it equal to 0. Remember, now we need to check in the second derivative if for those x values, right, if I substitute 10 over 3 into there, if my answer is going to be positive or negative. Remember, they asked you in this question for which the product is a maximum, okay? To find a maximum, right, we need to be dealing with a concave down, right? And a concave down means where the second derivative is less than 0. In other words, if we are right, then if we substitute 10 over 3, right, 10 over 3, this baby there, so 10 over 3 into the second derivative, we should get a negative answer. If we get a positive answer, well, that actually, then something's wrong. Then that answer is a minimum. So let's double check that. So 6 times by, what is that? 10 over 3. And therefore, that is equal to, so what's that? 10 over 3. And that is 4 plus of minus 40 plus by, what is that? 20. So the second derivative there of 10 over 3 is going to equal to negative 20. We've got a negative second derivative at 10 over 3. That means it's concaving down. That means we've got a maximum stationary point. Okay, the same story if I substituted 10, x is equal to 10 into there. So if the second derivative at 10 is then equal to, what is that then? So there we go. So it's minus 40 plus by 6 times by 10. And that means the second derivative at 10 is going to equal to, what's that? 60 minus 40 is equal to 20, right? And 20 is a positive answer. So the second derivative is greater than 0. That means it's concaving up. That means there's a minimum turning point. So that will be the minimum, and of course that makes sense. I mean, that's the most minimum x is going to get if you're thinking of two numbers whose sum is 10, right? With all the other constraints. So just to recap, what did we do? Okay, so let's just look at our little boxy there. So we looked at one of the constraints. Remember, they told us the sum of two positive numbers is equal to 10. So those are our parameters, right? And then what we do is we form an optimized function, right? So for which, so those the one of the two numbers multiplied by the square of the other one. So that's the product. For which is the product a maximum? So you write down that product, right? So the product px is equal to that, but you only want it in terms of either x's then or y's. Okay, you decide, it's up to you. If you just had it in terms of y's, of course you're going to have y first, and then you work out x later on, right? So and yeah, so then others you do simultaneous equations with those two. You get x or y alone, and you just substitute that into the other one. You get a function all in terms of x's or in terms of one variable. It depends on what the variable is, and you just go for it. All right. Okay, so the next example I'm going to do is determine the maximum area of a rectangle with a perimeter of 100 meters. I want you to try this quickly, so I want you to pause, see if you can set up the optimized function, right? And then you just double check on the video if you've got the right one, and then you just finding the derivative equal to 0, solve for those variables, and then just double check if your answer is positive or negative. All right. Okay, so let's quickly go through this. So the maximum area of a rectangle with a perimeter of 100. So what is our constraints, or the parameter? The parameter is the perimeter. I always confuse those two. But anyway, for some reason. So the perimeter of a rectangle is, so this is the length, and that's the breadth, or whatever. So it will be 2 length plus 2 breadth. Oh, goodness. 2 breadth is equal to 100 meters. Right, so that's the constraint we've got. So the perimeter is equal to 100, and then we want to know the optimized function must have the area. We want to know the maximum area of a rectangle. Okay, so let's look at this. So the area is going to equal to, what's the area of a rectangle? It's length times by breadth. Right, and now what you're going to do is you want to set up a optimized function where there's only one variable. Okay, so in other words, we either need to get length or breadth alone now. So if we get breadth alone, it's 100 minus 2 length. So therefore b is equal to 50. Oh, that's 50 minus l. 50 minus the length. And what you're just going to do now is substitute 50 minus l into b, of course, and then we have it just in terms of a. So a is equal to length times by 50 minus l. So therefore a is equal to 50l minus length square. Okay, and so therefore we've got an optimized formula. So in other words, AL, this is all in terms of L, not X, right? It's AL is equal to 50L minus L squared. Okay, so that's the optimized function. All right, and then what do we do with it? Well, we need to, how do we find the maximum? We're going to find the derivative of AL and let that equal to 0. So what is the derivative of AL? It's going to equal to 50 minus 2L. Equal that to 0 is 50 minus 2L. So 2L is equal to 50. Therefore, L is going to equal to 25. All right? And so therefore, what is the breadth going to be? So if the length is that, therefore the breadth is going to be 50 minus 25. The breadth then is going to equal to 25 meters. So in other words, to find, and if you actually think about this question, it's actually quite obvious. So I hate that word, but anyway. So here we go. So to find a maximum area, the length and the breadth must be the same. Actually, the best rectangle would be a square, right? So of 25 by 25, and then you get 625 meters square. So that will be the maximum area of if the perimeter is equal to 100 meters. Okay. Hopefully that makes sense to you. All right. Okay, let's look at example 3. A box with a square base is made to contain a volume of 108 cubic centimeters. The box must be open at the top. Let the base be x, the height be h, as shown in the sketch, and then they ask you to show that the total surface area of the box is given by that. So that will be your optimized function and they told you what you need to get, and then they ask you to determine the dimension for which the surface area will be a minimum. So that's quite easy. Then you're just going to let the optimized function be equal to 0 and you solve for x. And then the last part is determine the minimum outer surface area, and you just nick that into your function then, and and you get the total surface area. So let's go through this. I want you to maybe pause it, see if you can set up that optimized function, that a to the x is equal to x squared plus 432 over x, on your own. And just a hint quickly, total surface area is like if you would paint the box, right? All the areas that you would paint the box, and remember there's not a lid on top. Okay, so just pause quickly, see if you can find the total surface area on your own. Okay, so let's quickly go through it. So the total surface area, so you're going to get a couple of these ones, right? So this is a rectangular box, right? Square base, square base, yeah. It is a rectangular box. So there's going to be a couple of those those ones. Okay, those sides. And what's the area of that? It will be x times h, so that will be xh. The area of that part would be xh. How many of them are there? So the total surface area of this box is going to equal to, well, xh, and there's going to be 4 of them, right? So there's 1, there's 2, is this that part there, and that part there. So it's 4 times by xh. Okay, and then we've got that bottom part, right? We've got the bottom part there is x times x is equal to x squared. So that part there, and that is equal to x squared plus by x squared. So what we've got is the total surface area is equal to x squared plus 4xh. All right. But there's no h in this part there, right? What else do we know? Then they told you, okay, so that's the optimized formula that we want to take further, but they told you the volume of the box is 108 cubic centimeters. In other words, the volume, how do you find the volume of this box? You would find the area of the base times by the height, right? And the area of the base is x squared, and then h is the height. And what is the volume of this box? Is 108 is equal to x squared h. Okay, that's now neat, hey? Look at that. So in other words, if we get these, we either want x's or h in the total, in our optimized equation, right? So I think the best deal here would be to replace that h with that h, all right? In other words, h is equal to 108 over x squared. So what we're just going to do is we're going to do simultaneous equations. So that baby goes in there. So what we've got is we've got the total surface area then is going to equal to x squared plus 4x, and h is 108 over x squared. So total surface area therefore is equal to x squared plus by 4 times by 108 is equal to 432, right? And x divided by x squared is x. Okay, and then the last part, they wanted you to find the total surface area of AX, so therefore AX is equal to x squared plus 432 over x. Just very important here, you cannot do anything with this, right? You need to get to that answer. You can't manipulate this to suit that. I mean, you're not going to get any marks for that. So please don't do that. Okay, hopefully that's not too bad, eh? So the optimized formula, the parameter, and you do simultaneous equations just in terms of one variable. Okay, and then for question B, this is now where we're going to find the derivative of that optimized equation and let it equal to 0. Okay, so what's the derivative of that? It's going to equal to and to just make it a bit easier here for us, so that is x squared plus 432 x to the power of minus 1. Yeah, you don't want x on the denominator, remember that? So therefore it is 2x, the derivative of x squared is 2x, and that will be negative 1 times by 432 is negative 432 minus 1 from the exponent. Let that equal to 0. 432, and then that's over x squared, right? Add that on both sides. 432 over x squared is equal to 2x. Multiply by x squared on both sides, so therefore 432 is equal to 2x cubed. Then you want to get x ln, right? Divide by 2 on both sides, that's 216. What's the square root of 216? That is equal to the cube root, of 216 is equal to plus or minus 6. Okay, does it make sense for the length of the box to be minus 6 centimeters? No, that would be a bit hectic. So therefore x is going to equal to 6, right? And then so that will be the x value for which the box will have a maximum volume, and then you just find the corresponding y value. So if they ask you for the dimensions, so that's all the x or h or length or breadth or whatever you're working out. So that is 108 divided by 6 square, and 108 divided by 36 is equal to 3. So okay, so we've got there's x, there's h. Okay, So that's what they wanted there. Okay, and then last question, question C there. Determine the dimensions of, it says determine the minimum outer surface area. So remember the optimized equation, the total surface area was AX is equal to, what was it again? X squared plus by 432 over X. Right, and what is X in this case? X was 6, so it's A6 is equal to 6 squared plus 432 divided by 6, and therefore you're going to get, if you just move that all in your calculator, you're going to get 108 centimeters square. Okay, so yeah, that's it. So that's not, I don't think that's actually too bad. What's the most difficult part? Grade 12, the most difficult part is to get that. Okay, now can I just give you this tip? Most questions, there are some questions where they won't tell you what the total surface area is, but if for those questions that ask you, can you show that? You know, you can get 0 marks for this part, and you can get full marks for this part. Okay, for the next part, you're just finding the derivative of that. Okay, but this is actually not too bad. And even if you made a mistake there, we mark with that mistake, of course, in the next part of that question when you finding the derivative. The next example I'm going to look at is example 40 in your textbook. It's on page 132. Okay, let's go for it. So what you've been asked here is to sketch alongside shows the graph of f of x, and I always think it's good to have them in different colors. So let's make the graph of f red. So there's f. And we've got the graph of g of x, and let's make g blue. So it's that straight line there. Right. And what they're asking you is, so they give you the equations of both of those, and they said PQ is a line segment parallel to the y-axis. Okay, so that means it's got P and Q will have the same x values. Does that make sense? So if it's parallel to the y-axis, so that means they've got the same x value, right? Those 2 points, right? And on the right-hand side of the x-axis, in other words, the x value of that must be greater than 0, with P on F and Q on G. Determine the maximum length of PQ. So we want to now find the maximum length between these 2 points. Okay, so how would we normally, if I knew what x was, how would you find the y value, the distance? You would, I think what you would have done is you would have substituted the x value into f, and you would substitute the x value into g. All right, so that will be, in other words, what is that, f of that specific x value, and that is the g of that specific x value, and then you would subtract fx minus gx. Yeah, so if, for example, if that was 2, you would have worked out what is f of 2, substitute 2 into x cubed, so it's minus a third, times by 2 cubed plus 9, and then you substitute 2 into the straight line, the minus 4 times by 2 plus by 9, and you go the top one minus the bottom one. This is exactly what we're going to do now. So the distance, to set up our optimized equation, right, we're going to, it's a distance, and the distance is, in other words, f of x minus g of x, the function on top minus the function on the bottom. All right, hopefully that makes sense. The one on top minus the one on the bottom to find that distance. It's got the same x values, right? And what is the function on the top? It is this, so it's minus a third x cubed plus 9. And what is the function on the bottom? It is minus 4x plus by 9. So therefore, the distance is equal to minus a third x cubed plus 9 plus 4x minus 9. So therefore, the distance then is going to equal to the 9 minus 9 subtract with each other. So it's minus a third x cubed plus by 4x. So we can just say then, therefore, well, that is the distance in terms of x then is equal to a third x cubed minus a third x cubed plus by 4x. Okay, so that's our optimized equation. That's not too bad, eh? Remember, they share the same x values, okay? So that is the same. We've actually followed the same structure. We looked at our parameters. In other words, we know what fx and g of x is, so fx minus g of x, but we know what fx and g of x, we substitute into there, and bang, we've got an optimized equation. So what do we do now? So that's for the first step. That is like when they normally ask you, can you show that the distance is equal to that? Now what we're going to do is to find the maximum length. So to find the maximum distance, we're going to find what the derivative of d is and to equal that to 0 and solve for those x values. So what is the derivative of function x here? So we're going, what is 3 times minus a third is minus 1x squared. Hopefully that makes sense. And what is the derivative of 4x? That is equal to plus 4. Equal that to 0. And we've got x squared is equal to 4. All right, and then what is x then equal to? X is equal to plus or minus 2. And remember, they told you now we're only considering the one on the right. In other words, therefore x is equal to 2. So we only have one x value. And remember, if you've got two x values, if they didn't give you that part, then you just need to test with a second derivative test. Okay, to check it with a second derivative test. Remember, if the second derivative then at 2 is positive, then it's a minimum turning point. If the second derivative at 2 is negative, then it's a maximum turning point. Okay, but anyway, that's quite easy. So we find, so that's at x is equal to 2. Oh, remember I guessed correctly earlier. So that is 2 at x is equal to 2. That will be the maximum distance. But they actually ask you determine the maximum length. So in other words, how do I find the maximum length? Well, I've got the equation for the maximum distance. It's that minus a third x cubed plus by 4x. But now I know at which point. It is at the point when x is equal to 2. So it's equal to negative third 2 cubed plus by 4, 2 times by 2. So the distance at 2 is going to equal to, what is that? Minus 8 over 3 plus by 8. And what is minus 8 over 3 plus by 8 is equal to 24 minus, so 16 over 3 units. All right, so that is equal to 16 over 3 units is going to be the maximum length thing. How cool is that? Right, grade 12s, and then so the next couple of ones